Welcome to Unit 3, Derivatives. We'll start by talking about what a derivative is. And in particular, the next 3 videos are going to focus on finding a derivative using the limit definition, sketching the derivative using some intuition that you're going to build, and estimating the derivative given some data. You should remember from class that derivative is basically a tool for making predictions about change, but we need to be very precise. It's not just any old change. It's how one thing is changing with respect to something else. So these 3 images represent different scenarios we've talked about in the last couple weeks. In each case, something is changing. But can you identify what the 2 quantities are that are related to each other that are changing? Another way to put this question would just to be, can you identify the units that would measure change in each of these 3 scenarios? Great, so hopefully you identified that with the race car we would be talking about how distance is changing with respect to time. With the fruit flies we were talking about how population is changing with respect to time. And with the biker last night, we were talking about how elevation was changing with respect to horizontal distance. And that actually revealed that we don't always use time as a unit when we're talking about change. Often we do. So what if we talk about just a function here, stepping away from the real world examples? What would it mean to measure a function's change? Well, it would mean to measure how y is changing with respect to x. And you know how to do that. That's slope. In fact, this notation, which you're going to learn to love, delta y, delta x, really just means the change in y, or the units of y that change, per every unit of x that changes in a different direction. Now, you actually know how to do this. Calculate the slope of f of x equals negative x squared plus 6x, which is graphed here, at each of these following values. Start with x equals 1. Beautiful. Hopefully you realized that the slope at x equals 1 was 4. If you struggled with that, let me explain what the work would look like. If not, you can go ahead and do some of the other ones while I'm explaining. We start with the function. We want the slope at x equals 1. The first thing I know is that at x equals 1, the y value is 5, so that's just the point in question. But that's not the slope, that's the y value. So to find the slope, I need to use the limit definition, because we can't calculate the slope of a single point. So I set up the limit of the difference quotient. I plug in 1 plus h where x is in the original function. Make sure that you plug it into both x's, and don't forget to subtract f of 1 at the end. And then the rest is really just simplifying, and it should look pretty familiar by now. Hopefully this jogged your memory, so go ahead and calculate the slope at 2 and 4 if you haven't already. Beautiful. Here's the work if you just want to check yourself. As you should have seen in Edpuzzle, at x equals 2, the slope is also a positive 2. And at x equals 4, the slope is a negative 2. So think about what we just did for a second. We calculated how this function was changing at 3 different points. Think about the process we took and then the results, 4, 2, and negative 2. What would you observe about this process? Well, I have 3 observations. First of all, different points on the same function have different slopes. Second of all, even though the answers were different for each of those points, the work was pretty much the same each time that I did it. And actually, this is really annoying. It was the same thing over and over and over again. And I had to go through it because I didn't know how to get the slope, but it seems like there should be a better way. Let's talk about each of these observations in order, starting with number 1. It makes perfect sense that different points on the same function have different slopes. We can see it. That's what it means to be a curved line. But sometimes the most obvious observations can lead to actually really interesting places. So let's take a closer look at what we know. We know that at these 3 x values, the slope of f of x was 4, and then 2, and then negative 2. And I'm just kind of trying to jot down my thinking process. It seems like maybe a natural question to ask what would the slope be at 0 or at 3 or at 5? And I really don't want to go through that long process again, so I'm actually going to estimate it. I've got Desmos open here, and I'm going to estimate it just visually. If I go back to 1, which is approximately right here, I can see that the slope from this point along the green line looks like it's going up 1 over 4. So visually that confirms what we found numerically. Maybe I could do the same thing for 0. If I move the point and tangent line down to 0, looking at this line, we want to kind of guess what the slope would be. Well, I can see the line goes all the way up, and it looks like it's hitting right here approximately at 6. So that looks like up 6 over 1. I'm going to go ahead and estimate that at the x value 0, this function has a slope of 6. And then I'll do the same thing for 3. And this is just an estimate. We don't really know. But if I go over all the way to 3, watch how the slope of the tangent changes. Well, that's pretty clear. That's definitely looking like at 3, the tangent line has a slope of 0. And for good measure, let's go on and go all the way up to 5. So if I move the point over to x equals 5, we notice something really dramatically changing about the slope. Namely, the slope is now going in the negative direction. And when I try to figure out exactly how much, it looks like it's going down 4 over 1. So that would be a negative 4 slope. Look at these numbers for a second. What do you notice? What do you think the slope of the function will be at 6? Right, so hopefully you just saw that there's a pattern. And for some people, patterns are going to be easier to see if we create a graph. So I'm going to go ahead and graph these points. Again, remember I'm graphing the x value of the original function and the slope. So I'm not going to create a graph that looks like a parabola necessarily. 0, 6 would be right here. Go ahead and graph it for yourself, as will I. If you didn't see the pattern now, you should see it now, because these points really don't look random. They look suspiciously like a straight line, and it would be a straight line with a negative slope. Now, we don't really know whether I'm justified in connecting the dots here. We just know these slopes. In fact, we even estimated a lot of them. So really, we only know the 4 and the 2 and the negative 2. But there's something interesting going on. And I'm wondering whether there's a way to use this as a shortcut instead of doing that long limit process each time I wanted to calculate a new slope. Let's move on to the second observation, and then we'll come back to this idea. The second observation was that even though we got different answers for the slopes at different points, the actual work of solving the limit seemed pretty much the same. To jog your memory, this is what the work looked like. Each time we did this, the only difference was really that we plugged in a different x value. In all of these problems, the first one, the second one, the third one, we had a binomial that we plugged in for x, which meant foiling it out, distributing the negative, and distributing a 6. And even though those x values were different, the actual process was the same. Eventually some terms canceled, eventually we took out a GCF, and then we ended up with different numbers at the end. But I wonder if instead of plugging in x each time and getting a different FOIL problem, a different distribution, what if we just left x as a variable? And instead of changing the problem at the beginning with 2 plus h here, what if we just use that x value at the last step? That way, instead of doing the whole limit out each time, we could just use the x value at the end of the process. If that doesn't make sense, don't worry, this is new. Here's what it would actually look like, this idea that I'm proposing, leaving x in. We'd start with the limit of the difference quotient, and I've left the data up here, don't worry about that. Focus right here with me. Instead of changing x into a particular number now, I'm just going to substitute x plus h into the original function, leaving x as a variable and also leaving h as a variable. Notice that f of x is just normal f of x. It's the whole equation with x left in. And notice that I use parentheses because the negative in the middle is going to have to distribute. That's a super common mistake. Next step, I'm just going to simplify the difference quotient. You were doing it on delta math all day yesterday.